All right, I'm going to zoom in a little bit. There we go. Lecture 13. Number sets. Okay, so today we're going to talk about a bunch of different numbers. Some of them you know, some of them you don't know. But the ones that you don't know are called the imaginary numbers. And we're going to look at those more in depth next week. So we're going to spend today just looking at the number sets and how they all work together, how they're defined, what are their major characteristics, and how do you write the sets, what do they mean, things like that. That's what we're going to be talking about today. So first of all, I do want to get one quick thing out of the way. Let me define what a set is. Okay, a set. A set is a collection, an unordered collection of objects. It's just a collection of objects. Or instead of objects, we can call them elements. Has nothing to do with chemical elements like nitrogen or oxygen or anything like that. It's just a bunch of objects that are all kind of thrown together, and they all kind of share the same characteristics and stuff like that. Okay, let's do subset. Okay, so a subset is a set where each element is contained in another set. Okay, so what's a set and what's a subset? So I'm going to draw a quick picture of what I'm talking about. So imagine there is a set X, capital X, and imagine there's another set which contains set X. We'll call it set Y. Notice that every single element in X, whether it's an element little x or an element A or an element B, and I'll put element C right here. Notice that every single element in X also belongs in Y. So we say that X is a subset of Y. Because X is contained in Y. And the way we kind of write this in our notation is we're going to write it as X is a subset of Y. X is a subset of Y. So that's the way we write it. And this little symbol right here is called the subset symbol. So we have a set X and we have a set Y. X is fully contained in Y. So we say that X is a subset of Y. Okay. So I'll just leave that up there for about a minute, and we'll get to talking about the number sets and what do they mean, what are they used for, and stuff like that. Okay? But do know there are these things called sets, and some sets are contained in other sets. So we say that X is a subset of Y. okay? Because every single element in X is also contained in Y. All right. So the first set that I wanted to talk about is called the natural numbers. So let's get to that. Okay, the natural numbers. This is the first set we're going to talk about. The natural numbers is going to be all the positive whole numbers. All the positive whole numbers. So what are the positive whole numbers? Well, the first positive whole number is 1, right? We don't include 0 because 0 is not positive, right? So we're going to have 1, 2, 3, 4, and so on. I'm not going to list them all. There's an infinite amount of them, right? So the way we symbolize this is we use the symbol, and it's actually called a bold symbol. It's actually a capital N, but I write it in a bold fashion, and that's why there are 2 lines right here. This is going to be a capital N. So the N just stands for the set of all natural numbers. So the way I would write it is N is equal to the set containing 1, 2, 3, 4, ... Okay? So every single positive whole number is called a natural number. So this is the set of natural numbers. Here's an important fact. This is an infinite set, right? Why is it an infinite set? Because there's an infinite amount of elements in the set, right? Every single natural number, I can get a new natural number by adding 1 to it. So if I add 1 to 4, I'm going to get the next natural number, 5. If I add 1 to 5, I'm going to get the next natural number, 6. So the set of all natural numbers is indeed an infinite set. And every single set that we talk about today is going to be infinite. Infinite as opposed to finite, right? Okay. And the last thing I wanted to say about this was the natural numbers are countable. So let me write that down. The natural numbers is a countable set. And countable basically means that you can list all the natural numbers in a sequence. So can be listed in a sequence. Okay. One more thing before I leave the natural numbers. There are some people who believe that 0 is a natural number. I don't believe that, but there are some applications such as computer science and things like that where 0 is actually considered to be a natural number. But for our purposes in this class, 0 is not going to be a natural number. The way I think about it is, when you're a kid and you're learning how to count for the first time, you don't start off with 0, right? You don't say 0, okay, 1, 2, 3. No, you start off with 1, 2, 3. So 1 is the first natural number, and then 2 is the second natural number, and then 3 and 4 and so on. All the positive whole numbers make up the natural numbers. Okay? So I'll leave that up there for a few seconds so you can get it. And we will move on to the next number set, the integers. Okay. So if the natural numbers was the set of all positive whole numbers, then the integers are going to be all the positive whole numbers. But not only the positive ones, you also have to include the negative ones and 0. So let's talk about the integers. Integers is all the whole numbers. All the whole numbers, including positives, negatives, and 0. All the positives, all the negatives, and 0. So what does this look like? Well, usually the way we write the integers is we're going to go in two directions. We can go in the negative direction and we can go in the positive direction, right? So starting from the left, we're going to have 3 dots and then a comma and then -3, -2, -1, and then 0. Okay. 0 is neither positive nor negative. It's just 0. And then we get to the positive side. So 1, 2, 3, comma, ... And the dots just refer to all the positive whole numbers on the right side and all the negative whole numbers on the left side. So this is basically all the whole numbers. No fractions yet. We're only dealing with the whole numbers. So the symbol for this is going to be a capital Z, actually. And that sounds strange, but let me show you how I write it. So the symbol for the integers is going to be, you write a 7 like this, and then you write a backwards 7 or an upside down 7. And that's going to make it a capital Z. Okay? So why do the integers, why are they represented by a Z? Well, this is actually from a German word, Zahl, Z-A-H-L. Zahl is the German word for number. And of course, this is in German. Okay. So the way we would write this is Z is equal to the set containing ... -3, -2, -1, 0, and then +1, +2, +3, ... There's an infinite number of numbers in here, but I don't want to write them all, you know. You can't write down an infinite number of numbers, so we just put dots to represent the positive side and the negative side. So these are all the whole numbers. And of course, this is also an infinite set, so let me write that down. This is also an infinite set. It's an infinite set that contains all the natural numbers. So contains all the natural numbers. And the way we would write that is we would write it as N is contained inside Z. So the natural numbers is actually a subset of all the integers, right? All the positive whole numbers are contained inside the integers. So we say that N is a subset of Z. Okay? And we can also say that this is a countable set because all the numbers can be written in a sequence. So this is also a countable set. And eventually, when we get up far enough, the number sets turn out to be uncountable. You can't list them all in a sequence. And the first uncountable set we're going to get to is called the irrational numbers. But I'll save that for later. So this is also a countable set, just like the natural numbers. Okay? All right. Let's go on to the next number set. The next set of numbers is going to be called the rational numbers. The rational numbers. So now we're going to start getting into fractions. And you know how complicated those can be, so let's talk about it. Okay. Let's do the rational numbers. The rational numbers. Okay. As you know, rational is just another word that means fraction. So rational means fraction, or it could also mean ratio. And remember that a ratio is just a relationship between two numbers. So for example, a ratio could be 2 to 3, right? We would write that as 2/3. So it's going to be the set of all fractions. And when I say fractions, I mean something like P over Q, where Q cannot equal 0. Okay. Q cannot be 0 because if Q was 0, you would actually be dividing by 0, right? And we can't do that. So the rational numbers is a set of all positive fractions. So positive and negative. Let me get rid of that comma. It's the set of all positive and negative fractions, comma, including 0. So 0 is also a rational number, and we'll see why in a second. So the rational numbers, the symbol for this is going to be Q. And there is a reason for that, so let's write that down. The symbol for the rational numbers, the set of all fractions, is a capital Q, with a vertical line down on the left side. So Q. Q stands for, you probably guessed it, but Q stands for quotient. When you divide two numbers, you're finding their quotient, right? So that's why the symbol for all rational numbers is Q and not R. R actually stands for the real numbers, but we'll get to those later. So how do we write Q? Q is going to be equal to the set of all fractions, P over Q, where P and Q are whole numbers. They are integers, right? So P and Q have to be whole numbers, and Q cannot equal 0, as we previously mentioned. Q cannot equal 0, right? That is not allowed. So basically, it's the set of all fractions where you have a numerator and a denominator. Both the numerator and the denominator have to be whole numbers for this to work. They can be positive or negative whole numbers. P can be 0, that's fine, but Q cannot equal 0 because you'd be dividing by 0, right? So what are some examples of rational numbers? Let's get a few examples going. So the first fraction that comes to my mind is 1/2. Another fraction, maybe 2/3, but these are positive fractions, right? You could also have negative fractions, like -1/4 or -55 over 54. And also realize that whole numbers can be written as fractions. So 2 is a rational number, 3 is a rational number. Of course, the negative whole numbers are there also, and 0 is a rational number. So why are whole numbers rational numbers? Well, think about it this way, right? If I have a number like 2, I know that's a positive whole number, so it's also natural, it's also an integer, But it's also rational because we know that 2 can be written as 8 over 4, right? So think about it. 8 over 4 is a fraction, yeah, right? And 8 over 4 is equal to 2. So 2 must also be rational, right? And I'm running out of paper, so I'm going to have to get a new sheet of paper. So let's talk about the rational numbers a little bit more, and then we'll get on to the irrational numbers. So what's the last thing I want to say about the fractions? Well, we know that the set of all fractions is an infinite set, right? So we can also say that the rational numbers are an infinite set. They are also countable, right? The rational numbers are also a countable set. That means you can list them all in a sequence. So yeah, it's an infinite set, it's a countable set. So that's the set of all fractions, okay? Now we're gonna move on to the irrational numbers. So let's talk about those. Let's talk about the irrational numbers. Okay. So what's an irrational number? The irrational numbers are numbers that cannot be written as fractions. Numbers that cannot be written as fractions. Okay. So these are all the numbers that can't be written as fractions. So what's an example of something that can't be written as a fraction? How about pi? You ever heard of that before? You heard about that before? Probably in a geometry class or a lower level math class. Well, pi is an infinite decimal, right? It's an infinite decimal. It's equal to 3.14159265358 ... I'm not going to list all the digits. I can't because there's an infinite number of them, right? So pi is an irrational number because it cannot possibly be written as a fraction. Okay. What's another number that can't be written as a fraction? Square root of 2. Square root of 2, which is also an infinite decimal, 1.414 ... This also cannot be written as a fraction. So square root of 2 is irrational. And there's a video on my YouTube page where I prove that square root of 2 is irrational. Okay. What are some other irrational numbers that you've probably heard of? Square root of 3 is also irrational. Square root of 5 is also irrational. You can't write that as a fraction. And basically, the square root of any prime number is irrational. So square root of p, where p is prime. The square root of any prime number is also irrational, right? Now, what about square root of 4? I skipped that, right? What about the square root of 4? Well, the square root of 4 is actually 2, right? That's rational. Okay, so we can't include square root of 4, but square root of 2, square root of 3, square root of 5, all those numbers are irrational. And what's another example of an irrational number? Cube root. Cube root of 2 is also irrational. So there are a couple examples that we can talk about. And it's important to realize that the irrational numbers are real numbers. So, irrational numbers are real. Okay, that's a fact. So think about it this way. Let's say I had the set of all real numbers, right? Imagine that I'm holding a bag, okay? And inside the bag, I have the set of all real numbers, okay? Every single real number you can think of is located in this bag that I'm holding. Now what I'm going to do is I'm going to reach inside the bag and I'm going to pull out all the fractions. All the fractions, I'm just going to take them out. All the rational numbers, I just throw them away. And then what's left in the bag? It's the irrational numbers. All those numbers that cannot be written as fractions. Okay? So what's the symbol for this? The symbol for the irrational numbers, there's actually not really a good symbol for this. So we're going to use R take away Q. And this basically means all the real numbers, but you take away the rationals. So I can write it like this, where the real numbers take away the rationals, or I can write it like this. All the real numbers subtract away all the rationals. So I could basically write it either way. Okay? Another thing to say about this is also an infinite set. This is also an infinite set, right? There's an infinite number of irrationals. And this is the first uncountable set. This is an uncountable set because there's no way to list all these numbers in a sequence. Okay. This is the first uncountable set that you're going to run into. And another interesting fact about the irrationals is there are so many more irrationals than rationals. So let me write that down. There are, I'll just say many more, even though that's kind of vague. But there are many more irrationals than there are rationals. And I'll just leave it at that. Okay? So imagine the set of all real numbers. You take away all the fractions, all the rational numbers, and then what are you left with? You're left with the irrational numbers. And these numbers are strange, but they are real. They do exist. They cannot be written as fractions, no matter how hard you try. Okay? All right, let's move on to the real numbers. The real numbers. And I'll zoom in for this one. The real numbers. Okay, so what can I say about the real numbers? Well, it's the set of all rationals and irrationals. So this is the set of all rationals, all the rational numbers, and all irrational numbers. Every single number that you've learned since you were born is real. So this is the set of all rational numbers and all the irrational numbers. So what's the symbol for this? We're going to use a capital R, just like I showed you on the previous page. We're going to use a bold R, and the R stands for real. Okay. This is an infinite set. As usual, all these sets are going to be infinite sets, right? But it's also uncountable. It's also an uncountable set because there's no way to list all the real numbers in a sequence. Okay. Another interesting fact about the real numbers, I don't know if you've noticed it yet or thought about it, but every single real number has a decimal expansion. So all real numbers have a decimal expansion. So what's an example of that? Well, take pi, for example. Pi has a decimal expansion that's like this, right? It's a decimal number with a whole bunch of digits, right? So that's an irrational number, but what about a rational number like 1/2? I could write 1/2 as 0.5, right? 0.5000 dot dot dot, where all the digits are zeros. Okay, so we could write 1/2 that way. What about whole numbers like 2 or 3? Let's take 3 for example. 3 can be written as 3.0000000. So the zeros go infinitely long, right? So my point is, every single real number has a decimal expansion, right? So I'll just put it that way. Now, there is a number set that's even bigger than the real numbers, and that's what we're going to talk about next. So the last number set that we're going to talk about today is the complex numbers. The complex numbers. These are also known as the imaginary numbers. So you got real numbers, but you also have imaginary numbers. And we're going to talk about those. Maybe you've heard of these before, maybe you haven't. But Algebra 2 is usually the first class where people learn about complex numbers. Okay? So let's talk about it. What are the complex numbers? It's the set of all numbers that have a real part and an imaginary part. Okay. So these are numbers that one part is real, but the other part is imaginary. And we're going to talk about what that means in a second. Okay. So let's look at an example of a complex number. Every single complex number can be written in the form z equals a plus bi, where I is equal to the square root of -1. And a and b are real numbers. Okay? So let's talk about this. Z is equal to a plus bi. The a and the b are going to be real numbers. But the I is a special number that you haven't heard of before. I is equal to the square root of -1. Okay? So the complex numbers were made up so that you can actually take the square root of negative numbers, because you actually couldn't do that before the complex numbers were invented. But basically, the real part is going to be the A, and the imaginary part is going to be the BI. So let me write that down. Z equals A plus BI. The A is going to be the real part. So the A is going to be the real part, like I said, but the BI is going to be the imaginary part. Okay. The symbol for the complex numbers is a capital C with a line down the middle. and the C stands for complex. This is also an infinite set. It's also an infinite set. It's also uncountable set. And I'll leave it at that. Okay? So all the complex numbers can be written as a plus bi, where a and b are real numbers, but I is the imaginary number, square root of -1. Okay? So in the last 5 minutes of class, I wanted to talk about a little diagram that I like to draw on the board for the kids. So let's take a look at that. So the complex numbers can be written as a diagram. And I'll get a new sheet of paper to show you what that kind of looks like. Okay? So first of all, we start off with the natural numbers. And the way I'm going to draw it is, I'm going to draw it as a circle in the very middle of the page. So here's my circle, and all the natural numbers are going to be in this circle. So what's the natural numbers? It's all the positive whole numbers, right? So 1, 2, 3, 4, so on and so forth. All those numbers are in this circle, okay? But then we have a bigger set called the integers, right? This is the set of all negative and positive whole numbers and 0. So let's draw an even bigger set that contains n, and we're going to call it the integers, okay? So every single natural number is also an integer, right? You already know that. But then there's an even bigger set that contains both of these sets called the rationals. So I'm going to draw an even bigger circle. And we're going to call it the rationals, okay? So every single fraction, whether it's positive, negative, or 0, lives inside this circle, okay? And then you have an even bigger circle called the real numbers. So let's draw that. You have an even bigger circle called the real numbers. And that is symbolized with a capital R. So every single real number exists inside this circle. Now, some of them are irrational, like pi. So they're not going to go in the Q circle, right? Pi is going to be in the real numbers, but it's not rational. So I can't put it in this circle. But I can put 1/2 here. I can put -2/3 here, right? Because those are fractions. Positive and negative whole numbers like -3 or +2, that's a natural number, right? So all the natural numbers are in this little circle. There's an even bigger set called the integers that are in this circle. And then all the rationals are in this circle. And then you have all the real numbers, which are encompassed in this big circle. And then there's an even bigger circle called the complex numbers, right? So this is going to be an even bigger circle. So I don't even think this can fit on the screen. Yeah, I'm gonna have to zoom out for this one. So the complex numbers are in this circle, right? So complex numbers, what's an example of a complex number? 2 plus 3i. That would be a complex number, right? -5i. -5i. That would be an imaginary number, so it would be in the complex circle. But notice every single real number is also a complex number, right? So you could have 3 plus 0i. 0i, so the imaginary part doesn't even exist. So this is actually a natural number. But it does exist inside this complex circle, right? Now, you're probably asking yourself, okay, are there even bigger circles, right? Are there even bigger number sets that we aren't even talking about? And the answer is yes. There are even more sets. Some sets, they're even bigger than the complex numbers, like the quaternions. The quaternions. The way I would write these would be a plus bi plus cj plus dk. So these numbers have 4 components. You have your real part, your imaginary part, but then you have these additional 2 parts that are called j and k. And you even have bigger number sets that contain the quaternions. It's called the octonions. So these numbers have 8 parts. And you have even bigger number sets like the Sedenians. I don't know how to say it. But these numbers have 16 parts, right? And there's actually an infinite number of number sets, okay? So that's something for you to think about. Okay,